A telescope sits 1 million miles from Earth, at the Sun-Earth L2 point, wrapped in a sunshield, chilled to near absolute cold, yet sensitive enough to catch photons from the beginning of everything. The James Webb Space Telescope isn't an eye. It's the closest thing we've ever built to a reverse clock. On the 11th of July 2022, NASA released Webb's first deep field, a speck of sky you could cover with a grain of sand held at arm's length, crowded with thousands of galaxies, some so distant their light left when the universe was only a few 100 million years old. It didn't feel like a picture of space. It felt like a photograph of time, and it came with unease. Those early galaxies weren't supposed to look finished. Too bright, too massive, like finding a city where a campfire should be. With that little time, how could they grow up so fast? Maybe the temptation is to say the data is wrong, or the models are broken. But there's a stranger possibility. What if the pace of time itself was different back then? We've been here before. 1998 forced us to accept cosmic acceleration and name dark energy to keep the equations standing. Now Webb is pressing on something even more fragile. This is that journey, a journey to uncover a terrifying secret that has been hidden for millions of years. Following the data and asking whether the early universe didn't merely evolve faster, but actually lived faster. The field looks almost quiet at first. A dark rectangle of sky, a patch so small you could hide it behind a grain of sand held at arm's length, scattered with pinpricks and smears of light. Some are sharp spirals and ovals, already familiar kinds of galaxies. Some are thin arcs, stretched by the gravity of something massive that never appears directly. And then there are the almost embarrassing ones. Tiny reddish blurs that do not look like much of anything. If you were just scrolling past the image on a phone, you might not even zoom in. But astronomers did. They took one of those faint red smudges and split its light into colors. They watched where the familiar spectral fingerprints of hydrogen and other elements had slid. Lines that should have lived in the ultraviolet had been dragged down into the deep infrared, into the part of the spectrum Webb was built to hear. From that stretching, they read a single number called redshift. And from that redshift, inside the standard cosmological model, they reconstructed a time. The answer it gave was not recent. The answer said, this galaxy sent its light toward us when the universe was only a few 100 million years old. Not even 1 billion yet. A cosmos that, in our expectations, should still be mostly dark hydrogen and helium, still struggling to ignite its first long-lived stars, still far from building anything you would call a mature city of suns. And yet, in Webb's data, that smudge is bright. Not blinding, but confidently luminous. Its light suggests a mass in stars that belongs to something already well underway, not just beginning. Its structure, as far as we can tell at that distance, is compact and organized, not a loose, chaotic cloud. On paper, in the models that ran on supercomputers through the late 2010s and early 2020s, a galaxy this early in cosmic history should look more like a construction site. What Webb shows instead feels closer to a finished district. From the middle of the year 2022 onward, that feeling kept repeating. Webb's first deep images, released in July of that year, were followed by deeper exposures and targeted surveys. In preprints and journal papers, through 2023 and 2024, different teams reported the same broad pattern. Galaxies at redshifts, around 10, even pushing toward 14, appearing more numerous and more massive than the standard lambda cold dark matter simulations had forecast. Authors chose careful words. They wrote about tension with expectations, about puzzling abundances, about surprising stellar masses. One widely discussed study, led by an international group and submitted to a major journal, described a set of galaxies whose inferred stellar masses, if their assumptions hold, approached those of the Milky Way while the universe was still in its first billion years. not identical twins of our home galaxy, but uncomfortably grown siblings appearing long before the schedule allowed. If it were only one such claim, cosmologists could sigh, re-examine the data, adjust a prior, and move on. But it was not one. Across multiple independent Webb programs, with different teams and different reduction pipelines, there emerged a population that came to be nicknamed the Little Red Dots Compact, extremely red sources in the early universe that are brighter and often seemingly more massive than the community had braced for. Some of them may host voracious black holes. Some may be dense starbursts. Some may yet turn out to be imposters when the data sharpen. But taken together, they sketch a young cosmos that looks busier and more built up than the old simulations liked. To really feel how much of a shift Webb brings, you have to remember what came before. The Hubble Space Telescope could also stare deep. Its famous deep fields, built up from many orbits of exposure, showed us galaxies when the universe was only a couple of billion years old, and hints of even earlier ones. Those images already forced tweaks to theories of how quickly galaxies assemble, how violently stars form, how feedback from supernovae and black holes regulates growth. But Hubble's eyes were tuned mostly to visible and near-infrared light. Past a certain redshift, the most stretched, most ancient photons simply moved out of its reach. Webb pushes that boundary. Its mirror is larger, its instruments are colder, and its detectors are deliberately tuned to longer wavelengths. Where Hubble saw a sparse scattering of faint distant points, Webb reveals a thicker forest. Regions of sky that once seemed close to empty at the highest redshifts now bloom with newly revealed galaxies. It is not that these objects suddenly sprang into existence when Webb opened its golden eye. They were always there. We just did not have a way to hear them. The surprise is not merely that they exist, but how they behave. Some of the early Webb candidates for record-breaking distance have, on closer inspection, turned out to be somewhat less extreme. Spectroscopic follow-up has occasionally knocked a galaxy down from a headline-grabbing redshift to a more modest one, and better modeling of starlight and dust has trimmed a few estimated masses. That is how science is supposed to work. First you glimpse a shape in the fog, then you walk closer and realize exactly how large it is. Even after those corrections, though, the basic tension remains. Webb has revealed a stunning population of bright galaxies at surprisingly early epochs, as one team phrased it, with redshifts greater than about 10 and at least one candidate around redshift 14 that seems to be shining only roughly a few 100 million years after the Big Bang. Another analysis of Webb's early universe sample concluded that the structure and masses of some of these very distant galaxies, living only about 300 million years after the beginning, look as evolved as galaxies that have had on the order of 10 billion years to grow. And it is not only the galaxies themselves. In parallel, Webb and its partners have started to uncover quasars' bright beacons powered by supermassive black holes from similarly early times. Previous observatories had already found quasars at redshifts around 7, harboring black holes with billions of solar masses, which were difficult to explain within the standard picture. Now Webb is contributing to the discovery and characterization of even earlier and perhaps lighter, but still impressively large, black holes at redshifts around 10, embedded in small, red, compact host galaxies. Some of these black holes have masses tens of millions of times that of the Sun when the universe is only a few 100 million years old. They are not just present, they are already feeding heavily. You can imagine the early universe as a blank page gradually filling with ink. In the simplest version of the story, the first stars take shape after a few tens of millions of years, forming from pristine gas. Those first stars are massive and short-lived. They burn hot, they explode, they manufacture heavier elements. They stir and enrich the gas around them. It takes generations of such cycles, stars forming, living, dying, and recycling their ashes to build up enough heavy elements and dust to cool gas efficiently and form the rich, complex structures we associate with mature galaxies. Each generation takes time. Even the most short-lived, massive stars live for millions of years. Lower mass stars live far longer. Gas clouds need time to collapse under gravity, time to radiate away heat, time to settle into coherent, rotating disks. Even if you stack these stages as aggressively as physics allows, fitting multiple rounds of star birth and death, chemical enrichment, and structural relaxation into just a few 100 million years is a demanding task. That is why the Webb results feel, quietly, like a time problem. It is not that anyone sees a law of physics being violated in a single glaring flash. It is that the whole schedule of events seems overbooked. Early galaxies look as though they have squeezed more history into their allotted window than our models had budgeted. Early black holes seem to have grown to impressive size in what, on our cosmic calendar, looks like an uncomfortably short span. When cosmologists explain redshift to non-specialists, they often say something like, "The further away a galaxy is, the longer its light has been traveling. And because the universe is expanding, that light is stretched to redder colors." But underneath that simple phrase is a whole apparatus that turns how red into how long ago. We take the redshift, we insert it into equations based on general relativity and a set of cosmological parameters, and out comes an age in billions and millions of years. We treat that age as a measure of how much time the universe has had to work on whatever structure we are observing. Webb's early galaxies are not arguing with the idea that space has expanded. Their redshifts are real. What they are pressing on is the assumption that the amount of physical history that can fit between, say, 300 million and 1 billion years after the Big Bang is what we thought it was. If you want a human image for this discomfort, you can borrow one from a film that has already colonized our collective imagination of strange time. In that story, a crew lands on a world near a massive black hole. Because of the intense gravity, time on the planet's surface passes differently than it does far away. For every hour they spend on the ground, many years slip past for their colleague in orbit. When they finally return, they have aged by a few hours. He has lived a lifetime. In the early universe, we are not dealing with that exact kind of time dilation. But the sensation, looking at Webb's data, has a rhyme with it. It is as if those first few 100 million years managed to hold more events, more cycles of star formation and collapse, more growth of gravitational structures than our current mapping from redshift to time naturally allows. Our equations tell us one duration. The richness of what Webb sees hints at another. For now, most researchers stay with the conservative move. They keep the clock as it is and make the early universe sprint. They invoke heavier initial black hole seeds, more efficient star formation, more frequent mergers, denser environments. They turn every knob toward fast. There is a lot of room within established physics to do that. And many papers are exploring those options in detail. But if we insist that all the usual laws hold and that time has always flowed in the same way we now infer, then even this first chapter of Webb's story already stretches the Big Bang timeline close to its limits. Somewhere between the red smudges on Webb's deep images and the comfortable narratives we have told ourselves about a gently maturing cosmos, something does not quite line up. So the question that begins to flicker, softly and almost impolitely, is not, are the data wrong or is physics broken? It is stranger and more specific. If we keep the laws and keep the measurements and keep the universe about as old as we think it is, what, exactly, are we assuming about time itself in that young era? And if that assumption is even slightly off, how do we save the story without losing the thread of cause and effect that made the universe feel comprehensible in the first place? On paper, that thread of cause and effect is laid out with almost soothing confidence, like a strip of film unrolled across the floor, each frame labeled, each moment assigned a time. At the very beginning, there is no picture at all, only a frame that stands for something we do not yet truly understand. An initial state so hot and dense that our current physics blurs. A heartbeat later, in the first fraction of a second, space itself is stretching violently, energy condensing into particles, forces separating from one another. In the stories cosmologists tell, this opening is almost always described in quick, breathless strokes, as though the human voice is not built to linger there. After that first flash, the timeline slows just enough for language to catch up. In the first minute or so after the Big Bang, conditions are right for what is called primordial nucleosynthesis. Protons and neutrons, which had been knocked around in the earlier inferno, begin to bind into the lightest atomic nuclei. Out of that brief era come most of the universe's hydrogen and helium, and a trace of lithium. It is not much in terms of variety, but it is a crucial chemical anchor. Almost all the heavier elements that will later make planets and people are missing from this early palette. Those will have to be built later, inside stars, and that takes time. Slide further along the film strip and you reach a frame about a few 100,000 years after the beginning. Up to this point, the universe is hot and opaque, a glowing fog of charged particles and radiation tangled together. Light cannot travel far without being scattered. The cosmos is bright, but nothing like a familiar picture is visible. It is more like trying to look through the surface of the sundae. Then, as expansion cools the gas, a threshold is crossed. Electrons settle into orbits around protons, forming the first neutral atoms of hydrogen. Suddenly, light decouples from matter and begins to stream freely through space. That ancient light, stretched and cooled over billions of years, is what we now observe as the cosmic microwave background. A soft bath of microwaves coming from every direction in the sky. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, stumbled onto that background more or less by accident, picking up an annoying hiss in their antenna that turned out not to be pigeon droppings or instrument noise, but the afterglow of the Big Bang itself. That discovery gave cosmology an extraordinarily precise timestamp. Here is what the universe looked like about 380,000 years after its birth. Here is the temperature. Here are the tiny ripples in density that will later grow into galaxies and clusters. From that point onward, the film timeline has a fixed peg driven into it. Later missions sharpened those measurements. The Cosmic Background Explorer, whose key results arrived in the early 1990s, showed that the microwave background had exactly the subtle variations in temperature that theory had predicted. The Wilkinson Microwave Anisotropy Probe, starting work around the beginning of the 2000 decade, mapped those variations in finer detail. The Planck satellite, launched toward the end of that same decade, refined the picture even further. From their combined work, cosmologists extracted a set of numbers, the density of matter, the amount of dark energy, the curvature of space that together define the standard model of cosmology, the one often abbreviated as lambda cold dark matter. In that model, the universe today is about 13.7 or 13.8 billion years old. The precise value nudges back and forth as data are reanalyzed, but it lives in that range. The cosmic microwave background snapshot at a few 100,000 years, the formation of the first stars a few 100 million years later, the assembly of recognizable galaxies over the next couple of billion years, all of it sits on that backbone. You can draw it as a neat diagram that starts at a point, expands into a cone, and has little icons labeled first stars, galaxies, clusters, set at increasing distances along its length. In that picture, galaxies that look somewhat mature begin to make sense after a few 100 million years. By the time the universe is, say, 300 or 400 million years old, you can reasonably expect that some regions have collapsed early, formed stars efficiently, and begun to assemble disks and bulges. You might even allow a few overachievers, galaxies that form unusually quickly in rare, overdense patches. But the bulk of the cosmic cityscape is expected to be modest at that time. Small protogalaxies merging, star formation still ramping up, heavy elements only beginning to accumulate. The thing to notice is that this entire story is a story about time budgets. For a galaxy to look grown up in the way Webb suggests some of those early objects do, several things must have happened in sequence. First, gas must cool and collapse into dense clumps under gravity. That alone can take tens of millions of years, depending on conditions. Then those clumps must become stars, many of them massive and short-lived. Those stars need to live long enough to burn hydrogen into heavier elements and then die, often in supernova explosions that spew those new elements back into the surrounding gas. The gas, now seeded with metals, can cool more efficiently and implode again, forming second and third generations of stars, some of them lower mass and longer lived. Over time, orbits settle, random motions are damped, and a disk or spheroid takes shape, with spiral arms or smooth light profiles recognizable in later epochs. Each stage has characteristic timescales rooted in tested physics. You can speed some things up by making the gas denser or by changing details of how radiation interacts with matter. But you cannot, within the same laws that govern stars in the Milky Way, make a massive star live only 1,000 years, or compress all of stellar evolution into a heartbeat. Nuclear fusion proceeds at rates determined by temperature, pressure, and quantum tunneling probabilities. Gravity pulls on matter at a fixed strength, and orbits take a certain time to complete based on mass and distance. These are not arbitrary, adjustable knobs. They are the foundation on which everything else rests. That is why cosmologists talk about the time budget of the universe. Given a certain age at a given redshift, how much physical work can the cosmos plausibly have done by then? How many generations of stars can have come and gone? How much metal enrichment and dust production can have taken place? How much merging and structural settling can have occurred? Within the lambda cold dark matter framework, the answer to those questions is not a matter of taste. It drops out of equations that have been cross-checked in many different contexts. So, when Webb shows us galaxies at redshifts of order 10 or beyond that look, from their light, as though they have already burned through several cycles of star formation, acquired substantial stellar mass, and perhaps even formed ordered structures, it is equivalent to discovering that the universe has somehow overspent its early time budget. On the schedule drawn from the cosmic microwave background and expansion history, there simply should not have been enough hours on the clock yet. You can picture the whole thing as a single, compact day. Let the instant of the Big Bang be the stroke when a stopwatch starts. Let the current age of the universe be a little after minute 13 on that same watch, as one popular outreach image does. In that compressed metaphor, the epoch, captured in the cosmic microwave background, is a fraction of a second after the start. The formation of the first stars, a few 100 million years on the real clock, becomes the first faint glimmers, appearing within the first minute or two. Galaxies like the Milky Way, with spiral arms and settled disks, belong to later minutes. Life on Earth shows up embarrassingly late, in the last seconds before minute 13. Now insert Webb's early galaxies into that analogy. Some of them, as far as we can tell from their brightness and inferred masses, look less like makeshift camps and more like compact cities with a respectable skyline. Yet on the compressed day, they seem to be appearing around minute 1.5. Everything we thought needed many minutes, multiple rounds of building, demolition, and rebuilding, looks as though it has happened in the opening stretch. The temptation, when confronted with this, is to shrug and say, fine, perhaps they just formed faster. But for scientists, that phrase cannot be hand-waving. Faster how? Faster where? Which step, exactly, in the chain from hot plasma to rotating disk can be safely accelerated without contradicting observations elsewhere? If you decide that gas collapsed more quickly in the early universe, you must make sure that the same change does not overproduce small galaxies at later times. If you allow stars to form with extraordinary efficiency at high redshift, you must ensure that you do not run out of gas too early, or that you do not create too many heavy elements compared with what is measured in the intergalactic medium. If you invoke massive initial black hole seeds to explain early quasars, you must explain where those seeds came from and why they did not also leave obvious scars in the local universe. Every fix for the time budget has to pass a gauntlet of consistency checks. It is as though you are allowed to rearrange the scenes in a film, but you are not allowed to break continuity. A character cannot appear in two places at once. A building that explodes in one scene cannot still be standing in the next. The standard cosmological model is, among other things, a continuity editor. It tries to keep the storyline of the universe internally coherent from frame to frame. That is why the classic cosmic timeline diagrams are so reassuring. They show a smooth arc, from a hot, dense beginning to a cooling plasma, to the release of the microwave background, to the slow emergence of first stars, then galaxies, then clusters, Then the web of large-scale structure, all drawn with tidy spacing. Complexity increases gradually. Structure grows hierarchically, from small to large. The pictures often put the Big Bang at one end, a curtain of microwave background a little further along, then a blossoming of galaxies, and finally, somewhere near the present, a little symbol for Earth. Webb's data feel, visually, like someone taking the left half of that diagram and compressing the labels closer together. First stars moves nearer to the Big Bang. First galaxies moves closer still. Mature galaxies creeps backward along the arrow. The right-hand side, anchored by measurements from the microwave background, supernovae, and galaxy surveys, stays where it is. It is the early half that bends. In the Standard Model, the assumption that underlies this whole picture is that the way time flows, the relation between redshift and age, between how stretched the light is and how long ago it was emitted, is governed by a single continuous set of equations. Those equations, coming from general relativity, describe how the scale of the universe evolves with time given its contents. They do not have a clause that says, before a certain epoch, time works differently. The rules are applied uniformly from the earliest moments after the Big Bang to the current cosmic era. That uniformity is part of what makes the model powerful. It means that when you infer the age of a galaxy from its redshift, you are using the same time coordinate that describes the release of the cosmic microwave background and the acceleration of the universe's expansion. It means all your cosmic clocks line up, or ought to. So when Webb raises what looks like a time budget crisis, it does more than inconvenience a few simulations. It nudges us to ask how rigid that underlying assumption really is. If we leave the laws of physics alone, if we keep general relativity, keep the measured parameters from the microwave background, keep the successes of lambda cold, dark matter on large scales, but allow ourselves to ask whether the effective rate at which physical processes ticked through the earliest chapters was somehow different. Can we relieve the tension without breaking causality? Can we imagine a cosmos in which events still follow one another in a consistent chain, where causes still precede their effects? But the mapping from redshift to how much has happened is more subtle than a single neat curve. And if we do, would Webb's too old, too soon galaxies stop looking like continuity errors and instead become clues that our timeline, while accurate in length, may be missing something about how thick those first pages really were? The thickness of those first pages, after all, is not something we have ever measured directly. It is something we have reconstructed from the marks left on them, the way an archivist might guess the age of a document, from the color of the ink and the feel of the paper. When cosmologists talk about the age of the universe, it can sound as though someone was there at the beginning with a stopwatch, clicking it on at the Big Bang and glancing at it now and then to see how many billions of years have passed. Of course, no such clock exists. What we have instead are traces, patterns, relics that can be turned into time if you trust a particular model of how the cosmos behaves. We live surrounded by indirect clocks. Light itself is one of the simplest of these. A photon leaves a galaxy in the young universe, vibrating at a certain color. As space expands, the wavelength of that light is stretched. By the time it reaches us, what was once ultraviolet might have become visible, or what was once visible might have slid into the infrared. We call this stretching redshift. Measure how much the color has shifted, plug that into the expansion history prescribed by the Standard Model, and you get a number for how long the light has been in flight. Redder means older, farther, deeper into the past. It is important to notice the quiet conditional inside that. The redshift is an observable fact. We can see how much the pattern of lines in a galaxy's spectrum has moved. Turning that redshift into an age, however, is an inference inside a particular framework. It assumes that the way the universe has expanded between then and now is described correctly by Einstein's equations with a certain mix of matter and dark energy. It assumes, in other words, that the clock we are using is the right one. The cosmic microwave background is another clock, or perhaps more like a timestamp printed across the whole sky. When Penzias and Wilson picked up that broadband hum in the mid-1960s, they were hearing light that had last interacted strongly with matter when the universe was a few 100,000 years old. Later, satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and Planck turned that hum into a map. Tiny variations in temperature, one patch slightly warmer than another, carry information about how much the universe had expanded by that point, what it was made of, and how gravity had begun to amplify the first wrinkles in density. Those temperature patterns act like the tick marks on the face of a clock. Their size, their statistical distribution, their relation to each other, all combine to say, by the time this light went free, this much cosmic time had passed since the beginning. Change the amount of dark matter or the density of ordinary matter, and the pattern changes. Change the age, and the spacing of features shifts. It is an exquisitely sensitive chronometer, but again, its reading depends on assuming that the basic rules governing space-time have not changed between that epoch and now. Later on the timeline, another kind of clock appears in the form of certain exploding stars. Type 1 are supernovae white dwarf stars that reach a critical mass and detonate, rise, and fade in brightness in a remarkably consistent way. That makes them useful as standard candles. If you know how bright something truly is, you can compare that to how bright it appears and infer its distance. In the late 1990s, two teams used these explosions to trace the expansion of the universe over billions of years. They expected to find that expansion slowing down under the pull of gravity. Instead, the distant supernovae were dimmer than predicted, as though they were farther away than the decelerating model allowed. The simplest way to reconcile this was to accept that the expansion of the universe is accelerating, driven by something like a cosmological constant or a more general form of dark energy. In terms of timekeeping, this was a shock. It meant that the rate at which the cosmic clock ticks is not fixed. The expansion history bends in a way that had not been expected. Yet the response was not to throw out the framework of general relativity. It was to add a new ingredient to the equations so that the clocks, the supernovae, the microwave background, the galaxy distributions would agree with one another. Another family of clocks does not rely on candles but on rulers. In the early universe, before the microwave background was released, sound waves rippled through the hot plasma of photons and baryons. These baryon acoustic oscillations left an imprint, a characteristic scale, a preferred separation between overdense regions. That scale is fossilized both in the microwave background and in the later clustering of galaxies. Measure how that standard ruler appears at different redshifts, and you can reconstruct the expansion history of the universe in yet another way. Quasars, the luminous cores of galaxies where supermassive black holes feed, have been recruited as clocks too, in a more experimental sense. Their X-ray and ultraviolet emissions seem to be correlated in a way that might allow some of them to serve as standard candles across enormous distances. If that correlation holds without evolving over time, then quasars could help anchor distance and age estimates in regions of the universe that are otherwise hard to probe. They are more like strange, flickering wristwatches than grandfather clocks. But they are part of the same effort, to turn observed properties into measures of how long the universe has been doing what it does. There are other devices in this scattered set of timekeepers. The ages of the oldest star clusters, the cooling of white dwarfs, the rate at which large-scale structure grows. Each method has its own systematics, its own sources of error. That is why cosmologists are happiest when several independent clocks tell the same time. When the microwave background, the supernovae, the baryon acoustic oscillations, and the galaxy surveys all point to a universe around 13 and a bit billion years old, expanding according to the same curve. It feels like walking into a house and hearing every clock on the wall strike the same hour. But here is the quiet catch for the hypothesis we are circling. All those clocks, in one way or another, are calibrated inside the same architecture of space-time. The equations of general relativity define how the scale factor of the universe evolves given its contents. Lambda cold dark matter is one particular solution to those equations, with a certain density of matter and a certain vacuum energy. When we translate redshift into age, when we infer the look-back time from a supernova's brightness, when we read the acoustic peaks in the microwave background as timestamps, we are trusting that the structure of space-time in Einstein's equations applies smoothly from the earliest fractions of a second up to the present epoch. In other words, we are assuming that the style of time flow has not switched modes. This does not mean that nothing ever changes. The rate of expansion has changed. That is what the discovery of cosmic acceleration was all about. Galaxies have influenced one another. Dark energy has grown in relative importance. Structure has emerged. But underneath those changing contents lies the belief that the geometry of space-time itself, the way time and space are woven together and respond to energy and momentum, has followed a single, coherent set of rules. The cosmic clocks we use are all mounted on that same wall. The household analogy is simple. Imagine a home full of clocks. A digital one on the stove, a ticking one in the hallway, a cuckoo in the living room, the time display on your phone. Suppose they all agree down to the minute. It is tempting to conclude that they must therefore be telling the correct time. But if, for some reason, they are all set using the same faulty reference, if the time server they sync to is off, or if the mains frequency driving their circuits is slow, then their agreement tells you more about their shared assumptions than about external reality. Agreement is reassuring, but it is not infallible proof. Cosmology has not been blind to this danger. For decades, people have asked whether some of the constants that appear in physics might vary over space or time. The fine structure constant, a dimensionless number that measures the strength of electromagnetic interactions, has been a particular focus. Some studies of quasar absorption lines have claimed hints that it might have been slightly different in distant regions of the universe or in the deep past, while others have found no convincing variation. The community has not embraced changing constants as established fact, but neither has it treated the idea as heresy. It is something to be tested, bounded, worried at. You could see all of this as practice for the discomfort Webb is now provoking. We already live in a universe where the clocks forced us, in the late 1990s, to accept that expansion is accelerating and to insert dark energy into our equations. We already entertain, at least in the literature, the possibility that fundamental couplings might drift very slightly over cosmic time. We already use multiple, cross-checked rulers and candles and background glows to convince ourselves that our age estimates are not the result of a single, shared bias. And yet, beneath all of that, the assumption has remained. Whatever else changes, the relation between redshift and time, as given by our chosen solution of Einstein's equations, is globally valid. When we say that a galaxy at a certain redshift is being seen when the universe was, say, 500 million years old, we are using the same dictionary for time that we use when we say the microwave background shows the universe at a few 100,000 years, or when we say the oldest star clusters are nearly as old as the universe itself. Our culture has been quietly preparing us for more radical possibilities. We read stories and watch films where time is not a single, simple river. In one, an alien language rearranges a human mind so that past and future can be seen simultaneously. In another, cause and effect are tangled, events running forward and backward along different threads. In yet another, years pass on a mountain, while only hours slip by in a valley, or the other way around. These narratives do not teach the equations of general relativity, but they do something softer and maybe more important. They loosen our emotional insistence that time must behave in the most obvious human way. You do not need to understand the details of redshift integrals or metric tensors to grasp the key point. Every cosmic clock we have built, so far redshift, supernova light curves, microwave background ripples, baryon acoustic rulers, quasar correlations, is reading time under the presumption that the kind of time it measures is uniform in character from the beginning to now, not uniform in rate. We accept that expansion speeds up and slows down. Uniform in style. The same metric. The same mapping between this much redshift and this much look-back time. The same correspondence between a unit of cosmic proper time and what we think of as a year. Webb's two mature galaxies are not, by themselves, enough to overthrow that shared foundation. But they do something more subtle. They shine a cold, infrared light on the earliest chapters of our timeline and ask whether the clocks that have worked so beautifully for the later story might be misreading, in a consistent and undramatic way, the thickness of those first pages. If every clock in the house was set by the same slightly flawed recipe, you would not notice it by listening for harmony. They would all chime together. You would only suspect a deeper issue when something from outside the system, a broadcast from a more distant world, a signal that did not care about your household habits, refused to fit. Webb is not quite an alien broadcast. It is one more instrument we built, guided by the same physics and the same expectations. But by looking earlier, by pushing further back toward the beginning than any previous observatory, it is sampling a regime where our confidence is thinner. If all of our cosmic clocks infer early times under the assumption that time's style has been constant, then a telescope that peers into that regime and returns evidence of compressed history is not just adding a new number to the table. It is quietly suggesting that there might once have been a phase where the very manner of time's flow differed from what our equations, as currently written, allow us to imagine. If all those clocks were only slightly off, you could almost live with it. What makes it harder is when specific, concrete objects on the screen start shoving the tick marks on the timeline closer together, as if the film of the universe's history were being quietly compressed. One of the first shocks arrived in the middle of the year 2022, when a team led by Ivo Labbé sifted through Webb's early images and pulled out a small handful of galaxies that, by their analysis, carried as much stellar mass as respectable present-day systems, yet seemed to be shining only about 500 million to 750 million years after the beginning. 6 of these candidates appeared in their sample, all intrinsically red, all best fit by models where large numbers of stars had already formed and aged. In some interpretations, one of them nudged up toward a stellar mass comparable to that of the Milky Way, even if later work trims those numbers. The basic message is hard to soften. If those masses and redshifts are roughly right, then the universe managed to assemble big, quiet, heavy galaxies in what feels like the opening act. Around the same period, the JDES collaboration, the Webb Advanced Deep Extragalactic Survey, began publishing spectroscopic confirmations of galaxies at redshifts beyond 10. One of their standout objects, given the label JDES GSZ13, was confirmed at a redshift of about 13.2, meaning we see it as it was roughly 340 million years after the Big Bang. Later, even more distant siblings, with labels spoken as JADES GSZ14, followed. These galaxies are small in physical size but surprisingly bright in ultraviolet light, implying intense star formation in compact volumes at a time when, in older models, only the first faint structures were expected to flicker on. Put these results next to one another and a picture starts to form. On the one hand, you have candidate massive galaxies at redshifts around 8 or 9, already containing tens of billions or even 100 billion suns worth of stars. On the other hand, you have extremely young, extremely distant galaxies at redshifts around 10 to 14, pouring out light with a vigor that suggests extraordinarily efficient star formation. To make all of that happen inside the first billion years, the universe has to turn gas into stars with an efficiency that pushes close to theoretical ceilings. Some analyses, like Michael Boylan-Colchin's stress testing of the Standard Model, have argued that fitting the heaviest Webb candidates into lambda cold dark matter requires early star formation efficiencies, approaching something uncomfortably close to 100% in their host halos. In simulation land, you can respond to this challenge by turning the knobs. One option is to assume that the first reservoirs of gas in the young universe were denser and colder than expected, collapsing into stars more readily. Another is to populate the early cosmos with a top-heavy mix of stars, including many so-called population 3 giants, enormous, short-lived stars that burn furiously and seed their surroundings with metals in a cosmic blink. A third lever is the growth of black holes. If you allow the first black hole seeds to be very massive and let them accrete at rates that exceed the usual Eddington limit, super Eddington growth, you can grow billion solar mass monsters surprisingly quickly. Each of those fixes does something useful. Denser gas clouds bring down collapse times. Massive primordial stars accelerate chemical enrichment. Super Eddington black hole feeding makes early quasars less shocking, but each fix also tugs on other parts of the model. If the gas is that dense everywhere, later galaxies might end up overproducing stars. If population 3 stars are that common, their explosions and radiation could leave signatures in the intergalactic medium that we have not clearly seen. If black holes grow that greedily, they risk overshooting the masses we observe at intermediate times, or dumping too much energy into their surroundings. You can feel, reading the literature, how theorists are trying to satisfy two masters at once. Keeping the early universe wild enough to meet Webb's demands, yet calm enough later on to match the universe we actually inhabit. The more you dial the early conditions toward hotter, denser, faster feeding, the further you drift from the smooth, gently hierarchical picture that older simulations of lambda cold dark matter made famous. And then, as if the galaxies were not enough, there are structures like the one with the tongue-twisting name SPT2349-56. This object, seen through the combined efforts of the South Pole Telescope and the Atacama Large Millimeter and Submillimeter Array, is a forming galaxy cluster in the very early universe, its light reaching us from a time roughly 1.4 billion years after the Big Bang. Within a relatively compact region, astronomers find several dozen galaxies, many frantically forming stars, and a pool of gas so hot that, when they read its effects on the cosmic microwave background, it seemed to be at least several times hotter than standard models would predict for a cluster that young. The gas temperature and star formation frenzy make the system feel older than its age, as if, again, more history had been crammed into its allotted time than the usual script allows. To translate this into something that does not require a degree, imagine you are reading a recipe that says a loaf of bread needs an hour in the oven to rise and bake. You arrive at the kitchen 20 minutes in and find a fully risen, perfectly browned loaf already sitting on the rack. You can make excuses. Maybe the oven ran hotter than you thought. Maybe the dough was unusual, but at some point you have to ask whether your understanding of either the recipe or the clock is off. The community's first reaction has been to interrogate the recipe. Perhaps, some argue, we have underestimated how intense star formation can be in rare, early dark matter halos. Others explore whether the stellar initial mass function, the distribution of star masses, might tilt more heavily toward massive stars in the young universe, allowing for rapid light and metal production. Still, others test whether exotic ideas, like dark stars powered partly by dark matter annihilation, might lurk among Webb's extreme objects. At the same time, a small but growing set of papers has begun to use language that gives away the unease. Titles and abstracts talk about stress testing lambda-cold dark matter, about tension with lambda-cold dark matter, at high redshift, about early stellar mass densities contradicting the simplest version of the standard model. In conference talks through the years 2023 to 2025, slides have appeared with headings like the Webb tension, with plots where the observed points for early galaxies and clusters sit just outside the comfortable colored regions of the simulations. The mood is not panic. It is more like the feeling when a shoe that used to fit perfectly starts to pinch after a long walk. This is not the first time the cosmos has done this. In the late 1990s, the supernova teams found that distant Type 1a explosions were dimmer than they should have been in a decelerating universe, implying that cosmic expansion was speeding up. No one concluded that Einstein's relativity was useless. Instead, they amended the script with dark energy, a new term in the equations that allowed the clocks and rulers to stay in harmony. The parallel now is not exact, but it is suggestive. Once again, we have a model that works extremely well in many regimes. Once again, new data from a new instrument are pressing on a regime that had been poorly observed. Once again, the first impulse is to add patches, more efficient star formation here, heavier seeds there, a slightly different dark energy history perhaps. Some studies have even explored whether tweaking the dark energy equation of state, letting it evolve in time, could ease the abundance of early massive galaxies without demolishing the rest of cosmology. You can think of it like renting an apartment. On the listing, the place is advertised as having 30 square meters of floor space. The price seems reasonable for that size. When you move in, though, it feels bigger, more like 60 square meters. At first, you tell yourself it is just good layout, or that you are bad at judging area by eye. But then you start measuring, you pace out the rooms, you check against the length of your own body, maybe you even get a tape measure. Every time, the numbers come out closer to 60 than 30. At that point, you can keep insisting that the advertised number is correct and that everything else is an illusion. Or you can accept that the paperwork does not match the world you are standing in. With Webb, the paperwork is the time budget of the early universe, as calculated inside lambda cold dark matter. The measurements are the stellar masses, star formation rates, and gas temperatures of specific objects, candidate massive galaxies within the first billion years, compact, little red dot systems, hosting obscured black holes already active a few 100 million years after the beginning, and structures like SPT2349-56, whose intracluster gas is as hot, or hotter, than that in many present-day clusters, despite being observed when the universe was only about a tenth of its current age. Inside seminar rooms and over coffee, you can already hear people using phrases that nudge toward a different framing. They talk about effective formation times, about compressed early assembly, about squeezed timelines in their simulations. None of this is yet a formal change to the equations. It is more like an intuition that to make sense of Webb's results, they are, in effect, letting more happen per unit of cosmic time in those first few 100 million years than they used to. Our hypothesis simply says that quiet part out loud. Maybe the right way to think about the early universe is that its internal clock ticked differently, allowing a higher density of events inside what we, translating with our current dictionary, call a million years. The cultural imagination has already given us a character who lives in a world where time does not behave like ours. In one graphic novel and its film adaptation, Dr. Manhattan experiences his life all at once. Past, present, and future are laid out before him like panels on a page. He walks through them in a way that makes human notions of before and after feel provincial. Webb is not doing that. It is not revealing a universe where causality fails or where everything happens simultaneously. But by looking so far back, with such sensitivity, it is making our habit of assigning simple, uniform year counts to every era feel questionable. For now, the official stance is cautious. Many astrophysicists argue that when measurement uncertainties, selection effects, and improved modeling are fully accounted for, much of the apparent tension may relax. Some simulations already claim that, with clever enough recipes for star formation and feedback, they can grow galaxies nearly as massive as Webb's candidates within the standard framework. Others point out that a few extreme objects do not break a statistical model built to describe populations as a whole. But even in those more conservative papers, there is a recurrent concession. Explaining the brightest, heaviest early galaxies requires pushing several physical processes toward extremes simultaneously. You need near maximal efficiencies of converting gas into stars, rapid assembly of dark matter halos at the rare high-mass end, and feedback effects that somehow do not shut everything down too early. It is a universe that works very hard, very fast, right out of the gate. And so we arrive at a fork that is as much philosophical as it is technical. One path says, the early universe simply worked impossibly fast by our old standards. Every parameter was tuned toward haste. Star formation was wildly efficient. Black holes gorged. Clusters heated with remarkable speed. Given the underlying laws, that is just how things went, and we will eventually get used to the necessary extremeness of the numbers. The other path is more unsettling. It wonders whether the phrase, a year, in the first few 100 million years after the Big Bang is really equivalent, in any deep sense, to a year as we infer it now. It asks whether our cosmic clocks, all calibrated on the same assumption about time's style, might be slightly mislabeling the thickness of those early pages. If they are, then Webb's data are not simply revealing a universe that rushed. They are hinting at one that, in its youth, may have lived at a different tempo altogether. It is one thing to say the universe hurried. It is another to imagine that hurry as a different tempo of existence, a way of living time that does not quite match the units we casually write on a page. So here is the hypothesis, stated as cleanly as possible in the half-light. It is not that our clocks are wrong. It is not that redshift has been mismeasured, or that the microwave background has been misunderstood, or that someone accidentally bumped the cosmic stopwatch. The proposal is quieter and stranger. In the first few 100 million years, space-time may have allowed physical processes to unfold, with a higher density of events per unit of cosmic time than the density we infer today. When we say 1,000,000 years for that era, we might be naming a span that, in terms of how much can happen, is thicker than 1,000,000 years, as we experience and model them now. Picture time as a river running from some inaccessible spring toward a distant ocean. For most of its length, the river moves at a steady, contemplative pace. Leaves drift. Stones on the bottom are only slowly rearranged. If you measure off 1 kilometer along that calm stretch, the water that passes through does a certain modest amount of work. But rivers have moods. There are places where the bed steepens, where the flow narrows into rapids or plunges over a fall. Within the same 1 kilometer, the water can carve rock, throw up, spray, uproot trees, rearrange entire banks. The distance is the same. The work done is wildly different. In this metaphor, the hypothesis says that early cosmic time was like such a waterfall section. 1,000,000 cosmic years near the beginning might have contained more cycles of formation and destruction, more structural rearrangements, than 1,000,000 years in the later, calmer stretch we live in now. The total age of the universe need not change. We can keep our 13-point-something billion years, the shared agreement that emerges when the microwave background, supernovae, baryon acoustic oscillations, and galaxy surveys all consult the same equations. The suggestion is that the earliest slice of that age contained more physical history per nominal million years than our current bookkeeping assumes. We have not miscounted how many pages are in the book. We may have underestimated how densely printed the first chapter is. This sounds, at first, like it should collide head-on with relativity, which already gives us a vocabulary for strange time. In Einstein's theory, clocks in strong gravity tick more slowly than clocks in weak gravity. A clock carried deep into a gravitational well or pushed to high speeds experiences less proper time between two events than a clock left alone on a quiet hillside. We have measured this on Earth, with planes and satellites. We have seen it in the orbits of pulsars and in the signals from GPS systems. What we are playing with here is not a denial of that. If anything, it is a conceptual extension. Relativity says that the rate at which time passes depends on the geometry of space-time and on the path you take through it. The hypothesis says that in the early universe, the effective relation between microphysical evolution, things like star formation, black hole growth, chemical enrichment, and the cosmic time coordinate we now infer may have had a different character. Not that cause and effect were reversed, not that you could visit your own past, but that for the same increase in the cosmic time parameter, more could happen locally than our current models assume. There is a precedent for accepting an unreasonable phase in the cosmic story. We already believe, or at least seriously entertain, that in the very first blink of existence, the universe went through a period of inflation, a phase where space itself expanded at an astonishing, nearly explosive rate. In a tiny fraction of a second, the observable universe was stretched from subatomic scales to astronomical size, smoothing out irregularities and seeding the patterns we now see in the microwave background. Inflation is an idea born of mathematical necessity as much as of direct observation. It patches problems with horizon and flatness. Yet, it has been integrated, however tentatively, into the standard narrative. If we can accept that space had such a wildly different mode for expansion in its first moments, it becomes harder to declare that time must have behaved in a perfectly uniform way across all eras. Perhaps there was also a regime less extreme than inflation, but still distinct, in which the mapping between cosmic time and the pace of complex structure formation was skewed compared with later epochs. Not a second inflation, but a kind of temporal phase, where the universe's internal processes ran in a more compressed, high-intensity mode. You can see hints of this idea already in the language of many James Webb papers, even when the authors do not phrase it in terms of time. To accommodate massive galaxies and black holes appearing early, they increase star formation efficiencies in simulations, letting gas turn into stars with almost ruthless effectiveness. They allow larger initial black hole seeds. They adopt star formation histories that are steeper, more front-loaded than in older work. They speak of rapid assembly, of accelerated growth, of prompt enrichment. Taken individually, these are technical adjustments. Taken together, they look like a collective admission that early cosmic history is being made to work harder per unit time. Our hypothesis offers a unifying sentence for that scattered intuition. Time, in the early universe, effectively ran faster in terms of how much could happen inside each million-year interval. When translated into our present-day clock language, there are at least two ways to imagine this in more formal terms, even if we keep the details blurred. In one variant, the time metric itself changes by era. Space-time goes through a phase transition, not unlike the phase changes of matter. Just as water can be steam, liquid, or ice, each with different behaviors, though built from the same molecules, space-time might have an early time phase in which the relationship between its temporal and spatial components is slightly altered. In that phase, local processes such as gravitational collapse, star formation, and black hole accretion might proceed through more steps for each increment of cosmic time than they do later on. After some threshold, the universe cools or thins out enough that the metric settles into the form we now assume holds everywhere. In the other variant, the underlying space-time structure is unchanged, but our present-day inference about early time is distorted by the way we map redshift and other observables onto a single global time coordinate. It would be something like looking at a map of Earth that uses a Mercator projection. Distances near the equator are rendered fairly well, but near the poles, they are stretched grotesquely. If you took that projection too literally, you would think Greenland is comparable in size to Africa. In the same way, our conversion from redshift to years after the Big Bang might stretch or compress certain early periods, making them look thinner or thicker than they were in terms of the amount of physical history they contain. In the first picture, time itself has phases, like a river passing from calm stretches into rapids and back. In the second, time is continuous, but our ruler for measuring it is warped, especially in the earliest part. The rapids have always been there, but our chart underestimates how much work the water did as it rushed through. Either way, the point is not to throw out the Big Bang or relativistic cosmology. It is to allow for the possibility that the way we assign equal-length segments called years to all epochs might be an oversimplification, especially for an era we have only just begun to observe directly. You could imagine a conversation late at night in a quiet office, two screen-lit faces looking at the same set of plots. One of them leans back in their chair and says, "Look, we can fix this. We give the first black holes bigger seeds. We let them accrete above the Eddington limit for a while. We tilt the stellar initial mass function toward massive stars in high redshift halos. We assume the gas is clumpier than we thought. Add enough of those ingredients, and the galaxies will be fine." The other person shakes their head slowly. "We are adding characters to protect the script," they say. "Bigger seeds, stranger stars, more violent feeding. It is like adding secret siblings and lost heirs to keep a plot twist from breaking the story. What if the problem is not the cast, but the timeline? What if the years in that first act are not the same kind of years?" The first scientist frowns. "You cannot just change time," they say. "Time is the coordinate that keeps everything anchored. If you touch that, you risk breaking causality." you risk making the equations inconsistent with themselves. Maybe, the other replies, or maybe there is a way to let the early universe have a different effective tempo while keeping the same causal order. Inflation already told us that space behaved in an almost unbelievable way in the first sliver of a second. Why is it unthinkable that time, in the first few 100 million years, had a subtly different style that we are only now being forced to notice? There is a pause. The office hums. Outside, the sky is just sky, indifferent to their argument. These are not, to be clear, conversations that end with a triumphant slam of a chalk on the board and a new consensus by morning. They are exploratory. They test the edges of what is permissible within the mathematics. They probe whether a varying time metric, or a more complicated mapping between redshift and age, can be written down in a way that does not immediately contradict the many successes of the current model. From an existential point of view, the hypothesis has a particular flavor. It does not say that the universe is tricking us, or that all our efforts to tell its story have been in vain. Instead, it suggests that we, as latecomers living in the quiet part of the river, have been assuming that the whole journey has the same gentle flow. Webb's galaxies, with their surprising maturity, are like distant spray thrown up by rapids over a rise we cannot yet see. They are not asking us to abandon the river metaphor. They are asking us to recognize that its character changes. Importantly, nothing in this picture requires discarding the Big Bang. The idea that the universe had a hot, dense origin, that it has been expanding and cooling, that light from the early plasma now bathes us as microwave background, that large-scale structure grew from initial quantum fluctuations, all of this remains. Likewise, general relativity retains its role as the framework within which space-time responds to energy and matter. The hypothesis lives downstream of those commitments. It plays with the possibility that, within that framework, there was an early regime in which the connection between cosmic time and the unfolding of complexity was tighter, more intense than our current parametrizations capture. James Webb is the thing that forces this onto the table. Without Webb, the early universe would remain a blurred sketch. Hubble hints and ground-based surveys would still be consistent with a story in which the first billion years were a slightly busier version of what our models showed, but nothing more. The standard timeline's smooth arc from simplicity to complexity would be dented but not cracked. Webb changes that by delivering specific, well-characterized objects whose properties do not sit comfortably inside the old-time budget. Massive galaxies with old-looking stellar populations appearing within the first billion years. Compact, red, possibly black hole hosting systems, shining fiercely only a few 100 million years after the beginning. Protoclusters whose gas temperatures and star formation rates make them feel older than they are. Each of these, on its own, could perhaps be waved away as an outlier, a quirk, an error. Together, they form a chorus singing that the early chapters of the universe's life may have been more densely written than we thought. Faced with that chorus, we have choices. We can keep adding more intricate harmonies to the existing score. Exotic feedback prescriptions, unusual initial conditions, carefully tuned combinations of parameters that let the early universe sprint while the later universe strolls. Or we can entertain, however cautiously, the idea that the underlying tempo marking printed at the top of the page for that first movement was different. Not wrong. Not off by a crude factor. Different in style. The hypothesis that time in the early universe flowed faster, in this precise, technical sense of having a higher density of events per unit of cosmic time, is not the most conservative option. It demands new work, new mathematics, new ways of relating observables to underlying theory. It will have to face hard questions about how to maintain causality, how to keep the microwave background consistent, how to avoid wrecking the delicate successes of nucleosynthesis and structure formation. But it has a certain clarity that the patchwork alternatives lack. Instead of hiding the strangeness inside many separate adjustments, it acknowledges directly that the story feels too compressed and asks whether perhaps our notion of early time is what needs to expand. It does not overthrow the Big Bang, and it does not tear up Einstein's equations. It suggests that, for a brief but formative era, there may have been a regime of time behavior we have not yet written into the script. And James Webb, with its gold mirror sitting far from Earth in the cold, is the instrument whose quiet data are pressing us, gently but insistently, to consider that possibility. The unsettling part is not that the universe might have done something strange once, but that every time we look closely enough, it seems to have been doing something strange all along. And only now are we catching up. In the late 1990s, before dark energy had a name, two teams of astronomers were using Type 1, a supernovae, as sensible, well-behaved clocks. These explosions, the deaths of white dwarf stars that reach a critical mass and detonate, rise and fall in brightness in remarkably similar ways. Calibrated carefully, they act as standard candles. If you know how bright they truly are, you can infer their distance from how faint they appear. Combine that distance with a redshift, and you get a point on the cosmic expansion curve. Everyone expected that curve to show slowing. Gravity is attractive. The more matter the universe contains, the more its expansion should be tugged backward over time. The question was how much slowing there had been. Exactly. So teams like the Supernova Cosmology project and the High Z Supernova Search Team went looking for very distant Type 1, a supernovae, whose light had set out when the universe was much younger, and compared them to nearer ones. The answer they got felt like a slap. The distant supernovae were too faint, not by a huge factor, but by enough that, if the underlying assumptions were right, they had to be farther away than a decelerating universe allowed. In other words, the expansion of the universe had sped up. At large scales, space was not only stretching, it was stretching faster and faster. You could still tell the story in terms of time, if you liked. The cosmic clock was not ticking at a constant rhythm. The intervals between tick marks were getting larger. To keep Einstein's equations and all the other successful parts of cosmology, theorists added a new ingredient to the mix: a uniform energy density associated with empty space itself. They called it a cosmological constant, or more generally, dark energy. In practice, it was an admission that our understanding of expansion time was incomplete. Something in the equations that linked energy, curvature, and the rate of expansion had been missing, and the supernovae exposed the gap. This was not just a technical adjustment. It was an institutional reset of the clock. In the year 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion through observations of distant supernovae. The citation formalized what the community already knew. Our intuitive picture of a universe gradually slowing down had been overturned by a set of carefully measured, indirect clocks. Time, on the largest scales, was behaving in a way that had surprised almost everyone. Since then, dark energy has become a central character in cosmology, but a mysterious one. In the simplest version, it behaves like a true cosmological constant. Its density stays the same as the universe expands, its pressure is negative in just the right way to drive acceleration, and its equation of state parameter, the ratio of pressure to energy density, is fixed at a particular value. Observations of the microwave background, baryon acoustic oscillations, supernovae, and large-scale structure have all been used to test whether that parameter really is constant in time, or whether it might evolve. More recently, large surveys such as the Dark Energy Spectroscopic Instrument have begun to hint that dark energy may not be perfectly steady. Analyses combining millions of galaxy and quasar spectra with other probes suggest that the strength of dark energy's influence could be changing slowly over cosmic history, perhaps weakening with time. If that line of evidence holds up, it will mean that the expansion behavior of the universe has not only changed once, from decelerating to accelerating, but maybe changing still. That would make our cosmic time inference an even more subtle business. The clock we thought we had pinned down in the early 2000 decade would have turned out to be more like a barometer, sensitive to shifts in a component we barely understand. Lay that beside the long-running discussions about varying constants, and a pattern emerges. The fine structure constant, which governs the strength of electromagnetic interactions, has been probed using quasar absorption lines, galaxy emission lines, and other techniques to see whether it might have been slightly different in distant regions or earlier eras. Results so far mostly set tight limits, suggesting that if there is variation, it is very small, but the very fact that mainstream physics is willing to test immutable constants for possible drift shows how far we have already stepped beyond a static picture. Taken together, these episodes sketch a lineage of discomfort. First, the microwave background forced us to accept that the early universe behaved like a nearly perfect blackbody, with tiny ripples in temperature, a fossil from a time when matter and radiation were intimately coupled. That alone changed our understanding of what 380,000 years after the Big Bang meant. It anchored that moment with exquisite precision. Then, the supernovae forced us to admit that the expansion rate did not follow the simple deceleration many had expected, but instead bent toward acceleration. Later, ongoing observations have continued to probe whether the agent driving that acceleration is static or evolving, and whether constants we once thought sacred might in fact be flexible. Our hypothesis about early time sits naturally in that widening frame. If we are already comfortable with inflation, a phase where space expanded absurdly fast in a tiny sliver of a second, and with dark energy, a component that makes cosmic expansion accelerate billions of years later. And if we are willing to test whether constants like the fine structure constant have drifted, then the idea of an early regime where the relation between cosmic time and the density of events is different begins to look less like madness and more like the next logical question. Culturally, we have been rehearsing this for a while. Stories and films have trained us to accept that a short moment can contain years. In one, dreamers descend into nested layers of sleep, and time stretches differently in each layer. A few minutes in a van tumbling off a bridge holds hours in a hotel and decades in a snowbound fortress. In another, a character lives a whole life in a simulated world, while only a brief interval passes outside. Our emotional intuition, once stubbornly tied to a single, uniform flow of time, has been gently loosened by narratives, where the same span on the clock can carry very different densities of experience. Those fictions are not proofs, of course. They are mirrors held up to our fear and curiosity. But they make it easier, at least, to imagine a universe in which some chapters are compressed epics, stretches where more history happens per unit of time than elsewhere. When you hear that Webb finds galaxies whose apparent age in stellar populations and structure seems too large for their redshift, you have a ready-made metaphor. Perhaps those early hundreds of millions of years were written in dream time, packed with events. The important logical step is to see that Webb is not the first instrument to force clock revisions. The microwave background, discovered in the mid-1960s and mapped in detail in the 1990s and 2000 decade, anchored an early snapshot and made the Big Bang a precise, quantitative story. The supernova surveys of the late 1990s blew open the assumption that expansion must be slowing and inserted dark energy into the equations. The continuing scrutiny of dark energy's possible evolution reminds us that even the late-time behavior of the cosmic clock is under review. Webb adds a new pressure point, not by changing the total length of the film, but by fattening the content of the early frames. It suggests that the slice of time between, say, 300 million and 1 billion years after the beginning might be too thin for what we see squeezed into it. If we insist on treating those years as equivalent in their capacity for change to years later on. From this perspective, the hypothesis that early time flowed faster is not being pulled from nowhere. It is a way of aligning several layers of surprise. The first layer is observational. There are too many bright, massive, chemically mature structures too early, from galaxies to protoclusters. The second is theoretical. Simulations strain to reproduce those structures without turning the early universe into an implausibly efficient factory that would leave mismatched consequences in later epochs. The third is historical. We have already lived through at least 2 epochs where new data forced us to revise how we think about cosmic time. First, by anchoring it more precisely with the microwave background, then by bending its expansion curve with dark energy, and now perhaps by letting that dark energy vary. Place all of that into one story, and the idea of an early temporal regime, a waterfall section of the cosmic river, becomes a continuation of a pattern. Every time we add a new, more sensitive instrument, the universe responds by making time less simple. First, we discovered that there was a time before atoms, when the cosmos was a plasma. Then we discovered that the rate of expansion itself was changing in an unexpected way. Now we are discovering that the first billion years may hold more structure than we thought that interval could comfortably contain. In that sense, the hypothesis that those early years are not equivalent, in their thickness, to later ones is riding a current that has been flowing for decades. It is the same current that carried cosmology from a static universe to an expanding one, from a decelerating cosmos to an accelerating one, from eternal constants to constants we test for drift. Each deepening of our view has made time, at the largest scales, more intricate. The question Webb leaves hanging in the cold space beyond its sunshield is whether we are willing to follow that current one step further, to a place where the phrase, "the universe is 13.8 billion years old," remains true, but the internal tempo of those years is no longer assumed to be uniform, and where the earliest pages of the story are allowed to be far denser with events than the calm, late chapter in which we now sit and count them. If the earliest pages of the universe's story are that densely written, it is hard not to wonder what kind of characters had time to emerge between those compressed lines. For a moment, leave the distant, half-formed galaxies and come closer, into the quieter neighborhoods around ordinary stars. The question is no longer only whether galaxies grew up fast, but whether something like life could have found room to breathe inside such a schedule. In early October of the mid-1990s, 2 astronomers, Michel Mayor and Didier Queloz, announced that they had found a planet circling a star like the Sunday. On October 6, 1995, the world met 51 Pegasi b, a gas giant burning in a tight orbit around its parent star. And the modern era of exoplanets began. The planet itself was strange enough, a hot Jupiter whipping around its star in a matter of days, but the deeper shock was conceptual. For the first time, the sky's quiet points of light were confirmed to have worlds of their own, not as speculation, but as data. In the 3 decades since that announcement, the number of known exoplanets has climbed into the thousands. As of the middle of the decade we are now in, astronomers have confirmed around 6,000 planets outside the solar system, with thousands more candidates waiting in line for verification. They come in every variety imagination might allow, and a few it never considered. Scorched lava worlds hugging their stars. Puffy gas giants with dayside temperatures high enough to vaporize metal. Compact systems of small rocky planets locked in intricate resonances. Lonely giants drifting between stars. Among them are many that sit in what we blandly call habitable zones, distances from their stars where, under the right conditions, liquid water could exist on a surface. That does not guarantee oceans or continents. It simply means the energy budget is not obviously hopeless. Still, once you have a catalogue with thousands of planets and a subset with temperatures vaguely friendly to chemistry, the old philosophical question about how much time life needs becomes, in a quiet way, more practical. It shifts from, could life exist elsewhere, to, how often did the universe give itself enough time to try? Earth offers one data point. Our planet formed roughly 4.5 billion years ago. Geological evidence suggests that some form of life may have appeared surprisingly early, perhaps within the first billion years or so, after the surface cooled enough to carry liquid water. Multicellular organisms took far longer. Conscious beings capable of building radio telescopes and space observatories arrived only in the last thin sliver of that history. On Earth, at least, a great deal of time passed between raw rock and reflective minds. That is the story we know from the inside. Out beyond the solar system, James Webb is beginning to whisper the beginnings of other stories. One of the planets it has stared at most intently carries the catalogue name K2-18b. It orbits a cool red dwarf star in the constellation of Leo, about 124 light-years from Earth. From earlier missions, astronomers already knew that K2-18b is larger than Earth and smaller than Neptune, and that it sits in its star's habitable zone. What Webb adds is a more sensitive look at its atmosphere. By watching starlight filter through that thin shell of gas as the planet passes in front of its star from our point of view. In the middle of the decade, teams analyzing Webb's spectra for K2-18b reported hints of molecules like dimethyl sulfide and dimethyl disulfide, chemicals that, on Earth, are associated mainly with life, especially microscopic life in the oceans. The detection was tentative, the statistical significance modest, and follow-up studies have already complicated the picture, suggesting that the signal could be weaker or even absent when different instruments and models are used. No one is claiming proof of life. The debate is active, messy, and exactly as skeptical as it should be. But even as a maybe, K2-18b is unsettling in a familiar way. It says, the universe can, around an ordinary star not so different from countless others, assemble a planet in a temperate orbit, wrap it in an atmosphere, and perhaps fill that atmosphere with complex molecules that at least rhyme with the byproducts of life, all within the age of the Milky Way as we understand it. Webb is not looking at the first billion years there. It is sampling a much later chapter. But it is showing us that the production line for planets and potentially life-related chemistry is not an exotic, isolated trick. Now fold that knowledge back into the early universe, where Webb's deep fields show galaxies forming stars with ferocious efficiency, building heavy elements and dust quickly. Those heavy elements are the raw ingredients for rocks, oceans, atmospheres. If galaxies reached a certain level of chemical maturity earlier than we thought, then the universe as a whole may have become capable of building life-friendly planets sooner than our older models implied. In the language of the hypothesis, the question shifts slightly. If early cosmic time flowed with a higher density of events, then the delay between the Big Bang and the onset of life-friendly chemistry might be shorter in our numerical labels, but not actually short from the universe's internal point of view. It may be that what we call 2 or 3 billion years after the beginning, counting with a uniform yardstick, contains as much internal astrophysical history as a longer span would in the later, slower tempo regime. Think again of those films where time is bent for dramatic effect. In one story, a scientist travels to a world near a massive black hole and spends a few hours on its surface, while decades pass on the ship above. In others, like Contact or Arrival, the encounter with another intelligence reconfigures the sense of time entirely. Years are seen at once, messages loop backward, lives are experienced non-linearly. These narratives ask whether different minds might experience time differently. Here the question tilts. Not how other beings experience time, but how the stage itself, the universe, may offer different time phases for them to arise within. Perhaps, for early galaxies, the universe gave itself a high tempo, a concentrated burst of activity where star formation, chemical enrichment, and structure assembly all raced ahead. Later, as dark energy came to dominate and the cosmic web settled, the tempo shifted, becoming more like the slow movement of a symphony, a better setting for the delicate, low-power processes of biology and thought. From this perspective, the fact that Earth took around 4 billion years to evolve complex life is not a universal rule. It is one trajectory in one corner of one galaxy. Elsewhere, in regions that assembled earlier, around stars that formed from gas enriched by multiple generations of massive stars, the necessary chemistry may have been in place much sooner. If the early universe truly had a time-over-time phase, then a planet reaching biochemically rich conditions at what we would call 1 or 2 billion years after the Big Bang might not be racing. It might simply inhabit a thicker, more event-packed slice of cosmic time. To us, looking back with a single, uniform clock, such worlds would feel too early. We would say, but Earth took so long. How can life exist already over there? That feeling of paradox depends on assuming that all billions of years are created equal, that a billion years near the beginning is the same kind of span as a billion years now. If they are not, if the early river ran closer to rapids, then our intuition about too early has to be retuned. Of course, the data are not there yet to point to a specific biosignature in the early universe. It is hard enough to tease out potential life-related gases in the atmosphere of a nearby super-Earth. Doing the same for a planet in a galaxy at redshift 10 lies beyond our instruments for now, but Webb's combined roles mapping the frantic growth of early galaxies and sniffing the atmospheres of closer exoplanets like K2-18b make a single, layered suggestion. First, the universe seems very good at building complexity when given the chance. It throws together stars, planets, disks, atmospheres, and elaborate chemistry with apparent enthusiasm. Second, our planet's path from molten rock to questioning minds is not obviously the fastest possible. It is one example drawn from a much larger space of histories. Third, Webb's two mature galaxies imply that the period during which the universe first became capable of assembling life-friendly settings might have arrived earlier than we once thought. If you combine those three, you get a narrative that feels almost inevitable in hindsight. To build a cosmos with galaxies, clusters, stars, planets, and eventually beings who ask, why, the universe may have needed a time-over-time phase near the start. An era of intensified doing, where more structural and chemical work was accomplished per unit of cosmic time than in the long, slow breathing space that followed. Webb, by revealing how much was already in place in that first billion years, and by beginning to trace potential biosignatures in the current epoch, is pointing with both hands at that possibility. From where we sit, late in the tale, our calendars are steady. A year is a year. Seasons come and go. But in the deep past, where Webb listens to faint, stretched photons and to starlight filtered through alien skies, the universe may be quietly telling us that not all of its years carried the same weight, and that part of the reason life could arise at all was that, long before we existed to watch, the cosmos itself was willing to work overtime. It is one thing to say the universe worked overtime to build stars and galaxies. It is another to ask whether that same overtime ever reached the level of oceans, weather, and something that looks back. So, let's step in from the deep field and sit closer to home, in the softer glow around ordinary stars, where the question shifts from how fast did galaxies mature to how soon could a place like this have learned to breathe. Ikundated did. In the middle of the 1990s, the night sky was, in most people's minds, still divided into two categories: stars and imagination. Then, on October 6, 1995, Michel Mayor and Didier Queloz announced that they had found a planet circling a sun-like star in the constellation of Pegasus. The planet was named 51 Pegasi b, a hot Jupiter skimming so close to its star that it completed an orbit in only a few Earth days. The object itself was odd, but the real rupture was conceptual. For the first time, we had hard evidence that a star like the Sun could host a planet of its own, not as a philosophical guess, but as a measured wobble in the star's spectrum. That discovery, announced on that specific October day, cracked something open. It turned other worlds from poetry into a catalogue project. From 1995 to this present decade, that catalogue has thickened beyond what most of those first exoplanet hunters would have dared to predict. As of the later months of the year 2025, astronomers have confirmed on the order of 6,000 exoplanets, spread across more than 4,000 planetary systems, with over 1,000 of those systems hosting more than one world. Thousands more candidates wait in the queue. The sky has gone from a handful of known planetary orbits to a jungle of architectures. Among these thousands, a significant fraction live in what we call habitable zones, orbital distances from their stars, where, given the right kind of atmosphere, liquid water could exist on a surface. That phrase, habitable zone, is deceptively soothing. It does not mean habitable. It does not promise blue oceans or green continents. It only marks the band where energy and temperature are not obviously hostile to the chemistry we associate with life. Even so, Once you have not just one or two but hundreds of planets in such zones, the old question, how much time does life need, begins to feel less like speculation and more like a real constraint you could someday measure. Earth needed billions of years to go from molten rock to forests and mines. Does that represent a cosmic average, a lazy outlier, or something in between? This is where James Webb, having stared so far back in time that it made galaxies look too old, turns its mirror toward closer, quieter targets. One of those is the planet known as K2-18b. It orbits a cool red dwarf star in the constellation Leo, at a distance of roughly 120 light-years from us. K2-18b is larger than Earth, smaller than Neptune, and probably wrapped in a hydrogen-rich atmosphere. It sits in its star's habitable zone, making it a candidate for what some theorists call a Hycean world, a planet with deep oceans beneath an airy, hydrogen-dominated sky. When K2-18b passes in front of its star, a tiny fraction of the starlight filters through its atmosphere before reaching Webb. The telescope's instruments spread that light into a spectrum, revealing which wavelengths have been absorbed. In that pattern, teams led by researchers at the University of Cambridge and elsewhere reported signs of methane and carbon dioxide, and, more controversially, hints of dimethyl sulfide and dimethyl disulfide molecules that, on Earth, are associated almost entirely with life, mainly tiny marine organisms exhaling their metabolic waste into the air. Later reanalyses pushed back, showing that the evidence for dimethyl sulfide in particular was statistically fragile, sensitive to modeling choices, and not yet at the level of a firm detection. Science did what it is supposed to do. It hesitated, rechecked, refused to crown a maybe as a discovery. But even with the caveat lights flashing, something important had shifted. We were no longer asking whether Webb could sense mere atmospheres. We were asking whether it could catch the faint chemical accent of possible life on a world circling a distant star. Think about what that implies. In the quietest possible way, in a galaxy that also contains those impossibly early, massive, chemically mature systems, Webb has seen at high redshift, the same instrument is now reading the air of a planet only a little more than 100 light-years away, and debating whether it contains the breath of microbes. The universe is capable of building stars, planets, oceans, atmospheres, and potentially life-related chemistry around very ordinary stars. It did so here. It seems to be doing so elsewhere. Now lay that beside the fast track for complexity that Webb has revealed in the early universe. Heavy elements, dust, rich star-forming regions, the raw ingredients for rocky planets, and complex molecules appear to have come online earlier than we thought. If that is true, then the clock that measures the delay between the Big Bang and the possibility of something like life may be mislabeling that delay as short or long, in terms that are not quite honest. In our uniform clock language, Earth took roughly 4 billion years to grow from chemistry to consciousness, and the universe itself is about 13.8 billion years old. So, in round numbers, it spent about a third of its current age just getting one planet to the point where it could ask these questions. If we take that as a yardstick, then a biosignature seen on a planet 2 or 3 billion years after the Big Bang would feel absurdly early. It would trigger the same reflex as Webb's massive early galaxies. Too soon. The schedule is broken. It's just of the seed. But if, as our hypothesis suggests, the early universe contained a time-over-time phase, a regime where more structural and chemical work happened per unit of cosmic time, then the meaning of too soon has to be rewritten. A billion years in the waterfall section of the river may carry as much astrophysical history as several billion do later on the calmer stretch. The delay between origin and habitability may look brief on paper, but feel long in the internal life of the cosmos. Popular stories have been preparing us for this kind of double exposure. In Contact, the protagonist listens to a signal that has crossed vast distances and times, folding someone else's now into her present. In Arrival, an alien language rewires perception so that past and future blur, and a human life is seen not as a straight line, but as a complete, looping pattern. These narratives are about consciousness, not cosmology, but they share an intuition. The same amount of physical time can contain very different depths of experience, depending on the frame from which you see it. What we are contemplating with Webb is an extension of that intuition from individual minds to the stage they stand on. Perhaps the universe itself has had more than one temporal phase, a high-tempo early act, where galaxies condense, stars live fast and die young, and the periodic table fills out quickly. A slower middle and late act, where expansion stretches space ever more gently, and where enormous, cold intervals open up between clusters. We live very late in that story, in the slowed movement of the symphony. It is easy, from here, to project our tempo backward and imagine that the whole performance has been paced like this. Earth's 4 billion-year climb toward intelligence feels long to us because we live inside it. But it may not be a universal standard. In regions of the universe that assembled early, around stars born from gas already seasoned by multiple generations of massive stars, the chemistry needed for life could have been in place when the universe was very young in our counting. If early time ran with a thicker grain, if more cycles of collapse, fusion, explosion, and mixing fit into each nominal million years, then a planet reaching a biochemically rich state, at what we call 1 or 2 billion years after the Big Bang, might not be breaking any real schedule. It would be using a different chapter of the clock. From here, our instruments can barely glimpse the atmospheres of nearby worlds like K2-18b. We are decades away from directly probing the air of a planet in a galaxy that Webb sees as a red speck at redshift 10. But the logic does not have to wait for that measurement. If the universe can, demonstrably, mass-produce planets and atmospheres around ordinary stars, and if Webb's high redshift observations indicate that the factories for heavy elements and dust were running hot and early, then the idea of an early onset of life-friendly conditions is no longer fanciful. It becomes a natural consequence of the same overtime that built those too old, too soon galaxies. There is a paradox-shaped ridge running through all of this. On the one hand, our homeworld tells a story of patience bordering on indulgence. Billions of years of slow change, of continents drifting, of atmospheres shifting, before any creature first traced the sky with questions rather than myths. On the other hand, the universe seems, in its architecture, eager to produce complexity wherever it can. Galaxies assemble quickly. Planetary systems form in dusty disks as a matter of course. Chemistry sprawls into every niche that temperature and energy allow. If Webb is right about the early universe, if those first billion years contained more structure and metal and dust than we expected, then perhaps this paradox dissolves. The universe did not waste time. It invested heavily up front in a time-over-time phase that built the scaffolding for galaxies and the toolkit for life. Then, having laid that foundation, it shifted into a slower register, one in which thin films of self-replicating chemistry could persist long enough to learn and remember. From our perspective, sitting in that slow register, any hint of biosignature on a distant world feels both dizzyingly intimate and impossibly early. But that feeling rests on an assumption we are now obligated to interrogate: that all billions of years in the universe's history are equally thin, equally capable of carrying change. Webb's fingerprints on the early cosmos suggest otherwise. They suggest that for a while, long before we were here to count, the universe pushed itself, and that everything that came later, galaxies, planets, seas, the fragile conversations we have about them, grew in the wake of that ancient overtime. If the universe really did give itself an overtime phase, the most honest thing we can do now is to sit with that image and ask, very concretely, what would such a cosmos actually look like? Frame by frame, if time's tempo had once been different. Imagine, to start, that we keep all the familiar labels. We still say 500 million years after the Big Bang, 1 billion years, 13.8 billion years in total. The dates on the cosmic calendar do not change. What changes, in this thought experiment, is what those labels secretly contain. In the early era, for every million years that our present-day equations assign, the universe manages to fit, say, 2 or 3 times as many microscopic events, cycles, and transformations as a million years would accommodate later on. This is not a number we can currently compute. It is a sketch to guide the imagination. Think of an early million-year interval as a densely packed chapter in which the type is smaller, the paragraphs longer, the margins tighter. Later million-year intervals have larger print and wider margins. The page count of the book is the same. The amount of story per page is not. Apply that to galaxies first, because they are the clearest messengers in Webb's data. In a standard, uniform tempo universe, you might expect that in the span between, say, 300 million and 1 billion years after the beginning, a given region of overdense gas has time to go through perhaps 1 or 2 full generations of massive stars. Those stars form, shine, explode, enrich the gas with heavier elements, and stir turbulence into their surroundings. A second round of star formation then builds on that enriched material. By the end of the interval, you could plausibly have a young galaxy with some metals, some dust, and a still fairly chaotic structure. In the denser time scenario, the same nominal window could hold the equivalent of 3 or 4 stellar generations. Gas collapses, stars ignite, supernovae spray metals into space, and the enriched gas has time not only to cool and collapse again, but to do so more than once. Ordered structures like disks can emerge earlier because there have been more orbits in which chaotic motions can average out. From our vantage point, sorting galaxies by redshift and assigning ages with our uniform clock, we would call such a system too mature. From the universe's internal perspective, that galaxy would simply have lived through more internal history than our naive label suggests. Now turn that same lens on black holes. One of the puzzles that predated Webb, and has only sharpened with its data, is how supermassive black holes, with masses of millions or billions of suns, came to exist so early. To grow that large, a black hole has to feed. It pulls in gas, forms an accretion disk, and converts some fraction of the infalling matter's energy into radiation. That radiation pushes back on the inflow, setting limits known as Eddington limits on how steadily the black hole can grow. Even if you feed at that maximal rate, there is only so much mass you can add per unit time without violating those constraints. In a universe where early time has a higher event density, the language of per unit time becomes slippery. The same number of nominal years can hide more episodes of efficient accretion. In effect, the black hole is given more chances to approach its Eddington limit inside each million-year block. Short bursts of super Eddington feeding, which are hard to sustain in uniform time models, might fit more naturally if the medium around the black hole cycles between dense, cool infall and hot, feedback-driven clearing more often within the same labeled interval. By the time we see the object, hundreds of millions of years after the Big Bang in our counting, it has had not only those hundreds of millions of years, but the equivalent of a thicker internal record of growth episodes. Clusters, too, start to look less personally insulting under this hypothesis. Take that forming cluster with the cumbersome designation SPT 2349-56. In a uniform timeline, it sits about 1 and a bit billion years after the beginning and already hosts dozens of star-bursting galaxies embedded in shockingly hot gas. The gas temperature, inferred from its effect on the cosmic microwave background and from millimeter wave observations, seems comparable to that in much older clusters nearby. It feels, under the old script, like a teenager with the vital signs of a middle-aged person. If the early universe had a higher density of events, then many more mergers, shocks, and episodes of compressive heating could have occurred by that same 1.4 billion year label. The gas would have experienced more cycles of being stirred, compressed, and reheated by falling structures and active galactic nuclei. The fact that its temperature looks too old would simply be a sign that the cluster has lived a busier life per unit of cosmic time. Give the same labels to the frames, but fill the early frames with more collisions, and SPT 2349-56 stops being an anomaly and becomes a predictable outcome of a high-tempo phase. The key anchor through all of this is that, in modern physics, time is not a mystical river flowing outside of everything. It is a coordinate inside space-time, a dimension woven together with space. In general relativity, what matters is not some absolute, universal tick, but the geometry of space-time, the paths along which observers move, and the intervals they experience along those paths. Proper time, the time measured by a clock moving with an object, can differ between trajectories. Two clocks reunited after following different routes through a gravitational field can disagree. That flexibility is not a bug. It is part of why relativity works as well as it does. It opens the door, at least conceptually, to the idea that under extreme early universe conditions, the relation between the cosmic time coordinate we use in our equations and the rates at which microphysical processes unfolded could have gone through a phase change. We are not introducing a second magic time. We are asking whether, in the hot, dense, rapidly evolving primordial cosmos, the effective mapping between time, as we now infer it, and the internal capacities of matter and radiation to change might have been different. If that still feels too abstract, there is a gentler analogy much closer to home. Earth's biological history is not a uniform march. There are long stretches where change is slow, ecosystems are stable, and evolutionary shifts take tens of millions of years. And then there are eras like the Cambrian, where in a geologically brief interval, an astonishing diversity of body plans and ecological strategies burst into being. The fossil record thickens. More novelty appears per unit of time. It does not mean time itself sped up. It means that the interplay of environment, genetics, and ecology entered a regime where more innovation was possible in a shorter window. The overtime hypothesis for the universe is something like a cosmic Cambrian, but for time density. There may have been an era when the conditions for structural and chemical change were such that more could happen in each tick of the cosmic coordinate. Turbulent gas flows, rapid gravitational collapse, intense radiation fields, and perhaps differences in how effective microphysical processes were at redistributing energy and matter could all have combined to create a phase in which the universe's capacity to do things per year was heightened. Later, as expansion cooled and diluted the cosmos, as dark energy came to dominate, as the cosmic web settled, that capacity eased into a quieter regime. In scientific circles, of course, such an idea would not pass without friction. You can imagine one of those late-night discussions again, this time in the language of pedagogy rather than patching. "There is no such thing as faster time," says the skeptic, a bit exasperated. "You do not get to say that time sped up without specifying relative to what. Time is what clocks measure. If all the clocks agree, that is the end of it." In flash. "Maybe the issue is not speed but mapping," answers the supporter. "We are not claiming that proper time flowed differently along one world line than another in violation of relativity. We are asking whether our global coordinate, called cosmic time, built from a particular solution to Einstein's equations, might be assigning equal length labels to intervals that, in terms of how much structural evolution fits inside them, are not equal. The clocks are measuring the same coordinate. We may have misinterpreted what a unit of that coordinate means for processes sensitive to the early extreme conditions." The skeptic frowns. "That sounds like wordplay. If you cannot write it as a metric, it is poetry, not physics." "Perhaps," says the supporter. "For now, it is only poetry with some numbers whispering behind it. But if this mapping picture can be turned into a concrete modification of the early time metric, and if that metric makes Webb's galaxies, black holes, and clusters all fall into place without breaking nucleosynthesis or the microwave background, then we would be foolish not to take it seriously. Sometimes, the poetry comes first." He's prosed. "What about the consequences of admitting such a phase? One of the most immediate is that our habit of translating early epochs into a single linear years after the Big Bang number may be an oversimplification. When we say, with great precision, that a certain galaxy is being seen 600 million years after the beginning, we compress into that figure a long chain of assumptions about the expansion history, about the relation between redshift and age. about the constancy of dark energy on large scales, about the nature of dark matter. We write the number as though it were an obvious, homogeneous unit. In a universe with time phases, the statement 600 million years would still be correct at the level of the coordinate. But its experiential content, how much could physically have happened by then, would not be directly comparable to 600 million years in the current era. The neat line we draw across a diagram, with evenly spaced tick marks for each billion-year interval, would be more like a subway map than a to-scale survey, useful for navigation, misleading about actual distances and densities. That leads to the simplest philosophical question in this whole story, one that sits quietly under the technicalities. When we say the universe is 13.8 billion years old, what exactly are we claiming? Are we asserting that it has lived through 13.8 billion identical years, each one the same kind of slice, differing only in content? Or are we acknowledging, whether we realize it or not, that this single tidy number is a compression of uneven, possibly phase-dependent history into something we can write on a slide and share with schoolchildren? If early time once flowed with a different effective tempo for the building of complexity, then that familiar age statement becomes more like saying, "This book is 400 pages long," without adding that the first 50 pages are dense philosophy and the last 50 are wide-margined notes. The page count is true. The lived experience of reading is not uniform. For now, this chapter lives where it should, in intuition, not in equations. There are no new metrics written down here, no specific factors by which early time is stretched or compressed, no concrete proposals ready to confront data. What it offers instead is a set of pictures gentle enough to hold in the mind, a river with rapids and calm reaches, a fossil record with slow eras and explosive bursts, a universe whose years are not all equally thick. Those pictures are not proofs, but they make it a little easier to imagine that when Webb shows us galaxies and clusters that feel too old for their age, it might not only be because they worked impossibly fast, but because we have been assuming that the tempo of cosmic time never changed. If you listen long enough to any strange idea, the first thing you will hear is not applause, but the sound of careful people sharpening their objections. In the case of Webb's too old, too soon universe, the conservative explanations are not only reasonable, they are necessary. They are the way the community checks whether we really need to touch something as unsettling as time. One line of defense lives in the stars themselves. Maybe, the argument goes, we are not seeing too much stellar mass at early times. We are misreading how those stars are distributed. The initial mass function, the recipe nature uses to decide how many small stars and how many big ones to make in a given burst, is inferred from observations in the nearby universe. There, it appears to follow a fairly universal pattern. Many low-mass stars, fewer high-mass monsters. But in the dense, hot conditions of the early cosmos, the initial mass function might have been top-heavy, tilted toward more massive stars. Those giants shine very brightly and die quickly, enriching their surroundings with heavy elements. If early galaxies formed more of them than we expect, a given amount of starlight could correspond to less stellar mass than our local assumptions suggest, easing the too massive tension. Another line of defense focuses on black holes. The supermassive black holes powering the earliest known quasars are already millions or billions of times the mass of the Sun, when the universe, in our current counting, is only a few 100 million or a billion years old. That seems hard to achieve if you start from the depths of ordinary massive stars. So one proposal is to give those black holes a head start. Massive primordial seeds formed by direct collapse of gas, or even from more exotic processes such as primordial black holes birthed in the very early universe. On top of that, you allow them to grow not only at the usual Eddington limit, but sometimes above it, in super Eddington episodes where gas funnels in faster than the standard balance between radiation pressure and gravity would normally permit. Explained in plain language, these are all ways to speed things up without saying that time itself did anything unusual. A top-heavy initial mass function is like casting more sprinters in the race. Massive primordial seeds are like starting the runner halfway down the track. Super Eddington accretion is like letting them sprint faster than the posted speed limit for a while. You have not changed the length of the race. You have just stacked every advantage in favor of finishing early. Then there are the limitations of our numerical worlds. Simulations of galaxy formation and large-scale structure, even on the largest supercomputers, cannot resolve every detail of gas physics, star formation, and feedback. They rely on subgrid models, recipes that describe small-scale processes in average terms. It is entirely possible that some of those recipes, tuned to match the universe at later times, miss behaviors that become important in the first billion years. Increase the resolution. Refine the feedback. Include more realistic dark matter halo models and altered matter power spectra. And some of Webb's supposedly shocking galaxies may turn out to be less exceptional. Add to this the fact that Webb's surveys themselves are not neutral. They look at particular patches of sky, sometimes chosen because earlier telescopes saw something interesting there. The methods used to identify very distant galaxies looking for certain colors, fitting templates to noisy data, can be biased. Forward modeling studies have warned that, under some conditions, noise and selection effects can make galaxies appear brighter, redder, or more massive than they are. Spectroscopic follow-up has already revised some candidate record breakers downward in redshift or mass. It is entirely right to ask how much of the too mature landscape will survive once all the careful work is done. All of that is true. All of it deserves emphasis. The hypothesis about early time's tempo does not brush these objections aside. It grows in their shadow. Because if you strip those conservative fixes down to their bones, they all share a strategy. Every one of them tries to pack more events into the same nominal window. A top-heavy initial mass function? You are making more bright, short-lived stars per burst, which means more light, more supernovae, more chemical enrichment per million years. Massive primordial seeds plus super Eddington accretion. You are letting black holes skip the early, slow growth phase and then feast more quickly, so that more mass is gained per million years. More aggressive early feedback and denser gas in simulations. More cycles of collapse, ignition, and disruption per million years. Correcting for selection bias by arguing we have preferentially found the busiest regions. Again, you are concentrating a higher density of events into the part of the movie Webb happens to be watching. The objections do not reject the idea that the early universe was doing a lot in a little time. They insist on keeping time as it is and cranking up the doing. The hypothesis simply names what the fixes are already doing implicitly. It says, perhaps the reason you keep having to accelerate everything in your models is that the way you translate redshift into time for that era is not quite the right translation. Of course, there is another class of concern that sits even closer to the ground. Webb's instruments are new. Their calibrations are being refined. The pipelines used to turn raw counts into images and spectra are evolving. There may be systematic errors in how brightnesses are measured, how dust is modeled, how stellar populations are fit. It would not be the first time that an early release from a major observatory made the universe look stranger than it is, only for later work to recover a more modest picture. Yet, even allowing for that, the motif of too mature, too early, keeps appearing across independent analyses, different teams, different fields. The massive galaxy candidates, studied by Michael Boylan-Kolchin and others, do not come from a single survey. They show up in several, and their inferred masses push against basic limits set by how much baryonic matter is available in halos of a given size in lambda cold dark matter. Protoclusters like SPT2349-56 are found not in Webb images but in millimeter and microwave observations, yet they tell a parallel story of hot, assembled structures earlier than expected. The same theme keeps echoing. Systems that look older than their assigned slot on the timeline. When you zoom out even further, Webb's anomalies start to rhyme with another. Independent tension in cosmology. The mismatch between how fast the universe seems to be expanding, according to early universe probes, and how fast it appears to be expanding according to late time, local measurements. The Hubble constant, the number that encodes this expansion rate, comes out higher when inferred from Cepheid-calibrated supernovae and other nearby distance ladder methods than when extracted from the cosmic microwave background under the standard model. The discrepancy is on the order of several standard deviations, persistent across improved analyses and new data sets. This Hubble tension is not directly about James Webb, but it is about time. The cosmic microwave background ties the age and expansion rate of the universe together in one way. Local measurements tie them together in another. To make both right at once, something in our understanding of the cosmic clockwork has to give. Many proposed resolutions involve adding new physics in the early universe, an extra component of energy, a stage of modified expansion that changes how much time passes between the microwave background epoch and now for a given redshift pattern. In other words, some of the most serious attempts to solve the Hubble tension already play in the space of how cosmic time is mapped to observables. Seen from that vantage point, the Webb-driven need to push everything faster in the first billion years and the broader Hubble tension look like cousins. In both cases, we are faced with data that do not sit comfortably inside a single, simple timeline. In both cases, the first reflex is to preserve the existing mapping from redshift to time and adjust everything else. Our hypothesis does not deny those adjustments. It suggests that the repeated need for them may be a symptom of a deeper issue, that the time metric we are using as a backdrop might not faithfully represent the early regime. If you prefer something closer to the ground, think of a crowded city where everyone keeps arriving late. You notice that to get across town by 9 in the morning, you cannot just stroll. You have to walk quickly, maybe even run part of the way. Deliveries are rushed. Meetings start with people out of breath. Over time, the whole system adapts. Faster escalators, priority lanes, more intense schedules. You can frame this as people must learn to move faster. And in a sense, but if everyone, consistently, has to sprint just to meet a timetable written by someone who did not account for traffic, maybe the timetable, not the walkers, is what needs revision. In cosmology, the timetable is our mapping between redshift, cosmic time, and the capacity for structure to form. The conservative fixes to Webb's puzzles keep telling galaxies, black holes, and clusters to move faster. The hypothesis asks whether the schedule itself, at least in that early rush hour, has been drawn with the wrong scale. None of this is easy to turn into mathematics. To make the idea of an early time phase precise, you would need to write down a modified metric or an altered expansion history that respects general relativity, keeps the microwave background and nucleosynthesis constraints intact, and still allows for a different effective density of events per unit cosmic time in the first few 100 million years. You might need to invoke quantum fields in curved space-time, exotic couplings, or new behavior of dark sectors. It is a hard problem. It belongs in the domain where blackboards fill with symbols, and most of us, peering over shoulders, understand only the outlines. But difficulty, by itself, is not a verdict. Many of the ideas that now sit at the center of physics began life as things respectable people called absurd. The notion that Earth goes around the sun, not the other way, once ran against common sense and scripture. The idea that light has a finite speed and that this speed is the same for all observers initially sounded like nonsense. The prediction that time dilates, that moving clocks tick differently than stationary ones, felt like a trick of algebra. Each of these, over time, earned its place not by being comfortable, but by making correct predictions and tying disparate phenomena together. If a formal version of the early time-tempo hypothesis ever follows that path, it will not be because it is aesthetically pleasing, though it is. It will be because it can take Webb's two mature galaxies, early hot clusters, supermassive black holes at high redshift, and maybe even the Hubble tension, and show that they all fall naturally out of a single, slightly more intricate story of cosmic time. Until then, the strongest objections remain vital. They keep the idea honest. They remind us that noise, bias, and limited resolution are real. They insist that we exhaust the possibilities of top-heavy stars, hefty seeds, and better simulations before rewriting the background against which all of physics is drawn. Still, even while honoring those objections, it is hard to ignore the faint sense of pattern in the fixes. So many of them, in one form or another, are ways of admitting that the early universe seems to have done more in less time. Among all those patches, there is a strange elegance in the hypothesis that refuses to hide that feeling, that does not bury it under ever faster galaxies and ever hungrier black holes. It looks straight at the compressed timeline and says, softly, maybe the years themselves back then were not quite the same kind of years. It is strange to realize that by the time we arrive in the story, the loudest parts are already over. Tonight's universe, the one outside your window right now, looks almost calm from a certain distance. Star formation has slowed compared with its feverish past. Many galaxies sit in shapes they have worn for billions of years, their great disks and halos more or less settled into long, slow orbits. Clusters hang in space like vast, glowing archipelagos, and somewhere, inside a thin, spiral arm of one ordinary galaxy, on the surface of one small planet, a species that showed up embarrassingly late is counting all of this and calling it now. Against the backdrop of the whole cosmic film, humans appear in the closing frames. For nearly the entire runtime, there were no brains to imagine any of this, no cameras to collect ancient light, no hands to polish mirrors. The universe did most of its visible work before we were here to name it. If there was ever a time-over-time phase, a period when more happened per unit of time than our later experience would suggest, we are living long after it burned itself out. One picture that keeps returning is that of a construction site, only this one spans billions of light years. In the beginning, the universe may have rushed, not chaotically, but with a focused urgency. In that early regime, it quickly pulled matter into filaments and nodes, lit the first stars, forged heavier elements in their cores and in their depths, assembled galaxies from smaller fragments, and began drawing spiderweb patterns across the dark. Then, at some point, the tempo shifted. The scaffolding was up. The rough frame of the building was in place. The universe slipped into what we might call its slower chapter, a long period of finishing work and quiet detail. Star formation declined. The largest structures settled. Dark energy, that strange pressure in the equations, took over the expansion and gently stretched the spaces between the clusters, lowering the density, dulling the chances for new dramatic collapses. Delicate processes need such a chapter. The emergence of life and later, of consciousness is not an explosion but a lingering simmer. Molecules experiment. Cells stumble and improve. Ecosystems assemble, collapse, reform. On Earth, at least, nothing about that story looks rushed. If early cosmic time was a waterfall, perhaps this era is a lake, wide and reflective, where ripples can persist instead of being shredded. From our view, 1 second is 1 second. The watch on your wrist, the clock on your phone, the beating in your chest, all of them insist on a steady rhythm. But from the universe's view, if we dare to personify it for a moment, maybe we are living in the slow movement of a symphony that began with a furious opening. James Webb's two bright, two massive early galaxies are notes from that opening passage, still ringing faintly in the far distance, reaching our ears long after the orchestra has moved on to something more restrained. Certain dates have become markers along this arc, like timestamps on the corners of frames. On October 6th, 1995, 51, Pegasi B announced that stars like the Sun carry planets, not as myth, but as measurement. On some level, that discovery said, the universe did not only build galaxies, it built places where oceans might one day exist. In 1998, The dimming of distant Type 1, a supernovae, told us that the expansion of the universe was accelerating, forcing us to add dark energy to the equations to keep the clocks and rulers from contradicting one another. Time, at the largest scales, was already less obedient than we had wanted it to be. On July 11th, 2022, the first deep field from James Webb was released. That modest rectangle of sky packed with arcs and smudges and ancient red sparks. It looked like a photograph of time itself, stretched and crowded. Inside it lay galaxies, whose existence in such finished form so early quietly strained the timeline we had drawn. In the middle of this decade, K2-18b and its still contested whispers of dimethyl sulfide and dimethyl disulfide joined the story, reminding us that Webb is reading not only the farthest reaches of space, but also the thin skins of nearby worlds, where chemistry might be flirting with biology. Each of these waypoints has the same subtext. Every deeper measurement we make seems to push time away from the comforting, linear thing we would like it to be. The more precisely we try to measure it, the more it bends. In that light, the numbers we hold onto 1 million years, 1 billion years, 13.8 billion years in total, begin to feel less like direct descriptions and more like talismans. They soothe because they give us something to say. They give us a scale against which to measure our own lives and our civilizations. But if cosmic time has phases, if some intervals were thicker with events than others, then these tidy numbers are compressions. They put a smooth label over a jagged, uneven history. That is what this whole journey has been circling. We started with galaxies that looked too mature for their place on the calendar, systems whose brightness, structure, and chemical signatures seemed to imply more history than the standard timeline allowed. We listened to clusters whose gas was too hot, black holes that were too big, star formation that had run too fast. We noticed that the simulations kept trying to make everything more efficient, more aggressive, more on, in those first hundreds of millions of years, just to keep up with what Webb was seeing. We followed the way cosmology already had to revise its clocks, how the discovery of the cosmic microwave background pinned one early moment with unexpected precision, how the accelerating expansion announced that cosmic time does not behave as a simple deceleration, how the Hubble tension hints that our mapping between redshift and age might still hide surprises. We watched exoplanets and possible biosignatures creep into the picture, raising the possibility that life-friendly chemistry might have arrived earlier in the universe than our habits of thought would easily admit. Against that backdrop, the hypothesis that early time flowed faster, that it carried a higher density of events per nominal unit, does something very specific. It gathers scattered anomalies into a single question. Instead of treating each too much, too soon case as an isolated problem to be patched with more exotic stars, heavier seeds, or more violent feedback, it asks whether our translation between redshift and how much can have happened by then is subtly off for that earliest regime. If tomorrow someone produced a formal model that gave this idea mathematical bones, a modified metric, or an early time phase that preserved all the successes of Big Bang cosmology and still allowed a higher event density per unit cosmic time at high redshift, the physics would be the main story. But the narrative would change too. We would no longer tell children that the universe took a certain number of years to go from formless fire to galaxies, and then another certain number to go from galaxies to us, as though all those years were beads of the same size on a string. Instead, we might say, the universe began with a furious opening movement, where more happened in each beat than happens now. It built its scaffolding in a rush. Then it slowed, giving itself long, quiet spans in which things like continents, forests, and self-aware questions could appear. If, on the other hand, future data and better models gradually smooth away, Webb's anomalies, if masses shrink, ages recalibrate, and the galaxies of the first billion years slide back into line with a uniform tempo, then this hypothesis will fall away. It will take its place with all the other speculative ideas that briefly illuminated how limited our intuition is and then were folded back into more conservative stories. That 2 would be a kind of answer. It would say, even our most unsettling thoughts are subject to the discipline of new light. Either way, the exercise of imagining a universe with a time-over-time phase has already done something. It has made us conscious of how heavily we lean on numbers like million and billion to domesticate a reality that did not evolve to reassure us. It has made clear that our words for time, so grounded in the cycles of one planet around one star, carry a kind of provincial arrogance when we project them onto an entire cosmos. So the question comes back to you, quietly. If cosmic time does have phases, if some chapters are thick and others thin, some movements furious and others slow, does clinging to simple ranges and age estimates help you understand the universe, or does it mostly soothe something older and more fragile? The part of the mind that fears any story it cannot count? You do not have to answer that tonight. You do not have to pick a side between true and just metaphor, for the idea that early time flowed differently. For now, it can live in the same half-lit space as all good thought experiments. Near enough to feel, far enough to doubt. You can treat it as cosmic poetry, a way of making emotional sense of data that still bristle with error bars. You can treat it as a serious, if incomplete, physical proposal, waiting for equations and tests. You can treat it as a lens you put on and take off as you look at images from James Webb and ask yourself, how much history am I really seeing here? The universe will carry on either way, unconcerned with what stories we tell about its tempo. But if you allow the discomfort to stay with you for a while, the sense that those early galaxies, those hot clusters, those quick-born black holes, and those possible life-bearing planets might all be whispering the same thing about time, then the next sky you look up into may feel a little different. Less like a static dome, more like the afterglow of a performance whose first act we are only now beginning to hear. Maybe James Webb did not break physics. Maybe it only broke our comfort with time. And time never promised to match human intuition. When you see the next deep field, or the next spectrum from a faraway world, let that unease nudge you not toward fear, but toward paying closer attention, as if the universe, in its slower chapter, is quietly inviting you to listen for the echo of how fast it once learned to exist.